In this video we're going to consider an alternative way of expressing a complex number which is in something called polar form. And so thinking about what we've considered so far, we have talked about complex numbers in the form z equals x plus yi. But now we're going to say, rather than expressing that in terms of components, like x and y are the real and imaginary components, that can also be expressed in terms of what we call its modulus and its argument. Its modulus and its argument. And to clarify or understand what those two sort of characteristics or components of a complex number are, let's think about a complex number z in the Argand plane. So if this is z equals x plus yi, then that would mean that its real component there is x, and its imaginary component there is y. And so to understand the modulus and the argument, now it helps if we draw that line from the origin to that point in the complex plane where that number is represented, because that line, the direct line from the origin to that point, is the modulus. And so typically we use the letter r, so I guess that's really saying the distance of the point from the origin. And the argument is the angle that that line segment or that ray from the origin to the complex number, the angle that it makes with the positive real axis. Now, what we're going to get there is a right-angled triangle. We get a right-angled triangle in there. And so this is very much like vectors now. I'm thinking about polar form of vectors. But what we'd find is that in that right-angled triangle, well, cos theta would be equal to x over r. So therefore x would be equal to cos theta. And sine theta would be opposite over hypotenuse. That would be y over r. So rearranging that would give us y equals sine theta. And so we'll use those in just a moment. So let's talk about the modulus and the argument. So the modulus, well, we actually use our modulus or absolute value notation, which we've also used for magnitude. We've used it for determinant. So in this case, it means the modulus of a complex number, which is the distance of that complex number, that point in the complex plane from the origin. So we use the letter r. But in terms of its components, that would be equal to the square root of the square of the real component plus the square of the imaginary component, wouldn't it? So just using Pythagoras theorem there, be the square root of x squared plus y squared, where x and y are the real and imaginary components. That would be the modulus. Now the argument, so it sort of sounds like a funny name. I guess argument in some things, like in sort of computer syntax and so on, just means a sort of parameter or an entry. So here it's talking about the parameter, which is the angle. And we can see that theta would be equal to, well, tan theta would be y over x. So theta, we could think of it as the inverse tan of y over x. Now that's it's a slightly rudimentary result there, because I guess we do need to think about the fact that theta could be in a different quadrant, and so therefore there's two possibilities for tan being positive and two possibilities for tan being negative, and we'd need to make sure that we get the right one. So just like with vectors, we need to be a little bit careful with that. Okay, so polar form. Polar form, well, that's when we're converting from z equals x plus yi, so that's standard form or Cartesian form or rectangular form or component form. It's got lots of different names, and we're going to convert that into an expression in terms of r and theta. So we set up here that x is r cos theta, so up here I said x is r cos theta and y is r sine theta, so I could replace x with cos theta and y with sine theta times I, and I could take out that factor of r from both of those. Now, instead of saying sine theta times I, just to be clear that it's not the sine of theta times I, I'm going to put the I at the front and say I times sine theta. And then we've actually got this shorthand way of expressing that. So rather than saying r cos theta plus I sine theta, we just say r cis theta, where cis is shorthand for cos theta plus I times sine theta. So hopefully you can see where the C and the I and the S come from in that shorthand form. So that's called, this is called polar form, or mod arg form, or even sometimes just r cis theta form. So all of those, polar form, mod arg form, r cis theta form, all of those are an indication that we want to express the complex number in terms of sort of its distance from the origin and the angle that it makes with the positive real axis. So let's consider a particular example here where we could convert from one form to another. So this is from the exercise. Let's go question 1c. We've got this complex number z equals negative 2 root 3 plus 2i. Now, because of the ambiguity of just going inverse tan to work out our angle, just like with vectors, I think you always want to do yourself a little sketch. This one here, negative 2 root 3 plus 2, that's going to be in quadrant 2, isn't it? So negative 2 root 3 plus 2, so let's say plus 2, so that's going to be our complex number there. So the angle that we want to find is that one there, but using our right angled triangle, we're actually going to find this angle in here. So I'll call that one alpha, and then we'll take that away from 180 to find theta, or the argument of z. So first of all, r is just going to be equal to the square root of 2 root 3 squared plus 2 squared. And 2 root 3, that's 4, or squaring that is 4 times 3, so that's going to be 12. 12 plus 4, so it's going to be the square root of 16, which is equal to 4. And then, oops, and we could also say alpha is equal to the inverse tan of 2 over 2 root 3, whoops, 2 root 3, so that's the y component over the x component. So I'm not worrying about the fact whether they're positive or negative. I'm just saying in that right angle triangle, the opposite side has a length of 2, the adjacent side has a length of 2 root 3. So that simplifies to inverse tan of 1 on root 3. And that is, what's that? That's pi over 6, isn't it? So pi over 6. So that's the alpha angle. So therefore, we could say, therefore, arg z equals theta equals 180. I shouldn't say 180, should I? Because I'm talking in radians. I should say not 2 pi, just pi. So pi radians minus pi on 6, which is going to be 5 pi on 6. So therefore, I could say z is equal to 4 cis 5 pi on 6. So there it is in polar form. Now I should just say one more thing here before I mention a couple of other results, and that is that there are, of course, an infinite number of possible arguments, because we can just go coterminal angles. So, for example, so I could note, for example, that if arg z equals pi on 6 would be one possible thing, that would also be equal to, if I went 2 pi plus pi on 6, which would be, what's that, 12, 13 pi on 6. because they are coterminal angles. So pi on 6 and 13 pi on 6 are coterminal angles. So because of that, there are an infinite number of possibilities there, but the convention is that we use the principal argument, and so the principal argument is convention is to use the principal argument which would be between negative pi and pi, and we use uppercase A to indicate that. Just before we finish up here, a couple of things which are going to be useful for us, results with working with polar form. And in fact, it is a lot easier to multiply and divide complex numbers in polar form than in component form or Cartesian form. So let's say we had two complex numbers in polar form, and we could set up some brackets around that just to be clear. So we'd say Z1 is R1 cis theta 1, and the second complex number Z2 had a modulus of R2 and an argument of theta 2. Then the product of Z1 and Z2 would be given by taking the product of the two modulus of those complex numbers, and the argument would be the sum of the two arguments of those numbers. And for division, so Z1 divided by Z2, we would have R1 divided by R2 would be the modulus of that new complex number, and theta 1 minus theta 2. So as you can see, they're quite easy to multiply and divide complex numbers in polar form.